Designing subdivision roads often requires a comprehensive knowledge of compound and reverse curves. Let's look at a simple example using a cul-de-sac that would be part of a small subdivision. Many of the road parameters, such as minimum width of the road and minimum radii, are found in subdivision ordinances. In our example, the cul-de-sac will comply with the minimum road design criteria found in ordinances. The minimum width of the right-of-way is 50 feet in this town. The minimum length of a curve radius is 150 feet measured at the center of the road. The minimum radius for the outside edge of the right-of-way for a cul-de-sac turnaround is 60 feet. The minimum radius for a transition curve is 20 feet. Safety design requirements demand that roads intersect as near as possible to 90 degrees. This allows the driver to easily look in both directions before entering the intersection. The cul-de-sac road that is shown intersects the existing road at 90 degrees. Optimum design for the road indicates a delta angle to be 54 degrees 10 minutes 10 seconds for the center of the curve, starting at the existing edge of the right-of-way and going to the tangent extension for the cul-de-sac. The center of the cul-de-sac turnaround is located on a forward tangent to the center of the curve. The layout of the cul-de-sac that is shown does not include any transition curves. Transition curves are required to allow for a smooth transition by an automobile when changing direction. Without the transition curve, an automobile would either have to turn sharply when changing directions or trespass on private property. Transition curves are now added along the right-of-way of the cul-de-sac. Next, the points of curvature, points of tangency, tangent to compound points, compound to tangent points, points of compound curvature, and points of reverse curvature are marked. The points are numbered, so the identity of the curve can be made by reference to the numbers at each end of the curve. As seen in the diagram, our entire cul-de-sac is composed of reverse and compound curves. After locating these points along the curve center should be located. The center of the cul-de-sac is the easiest to locate. It is at the end of the forward tangent. Since the large curve starts at the edge of the road right-of-way that has an intersection of 90 degrees, the center of the large curve must be located along the edge of the road right-of-way, since the angle to the center of the curve from either the start or end of the curve is always 90 degrees from the curve's tangent. Measuring the radius distance of 150 feet from the center of the road along the road right-of-way will locate the center of the large curve. This is the center for both curve 2 to 3 and curve 6 to 7. The center of curve 1 to 2 is located applying curve principles. The angle from point 1 into the center must be 90 degrees from the tangent, in this case the edge of the road right-of-way. The radius for the transition curve is 20 feet. Measuring an angle of 90 degrees from the tangent and a distance of 20 feet along the line, and also 20 feet from point 2, locates the center of curve 1 to 2. Curve 1 to 2 and curve 2 to 3 are a compound curve. Therefore, the radius of curve 1 to 2 must coincide with the radius of curve 2 to 3. Curve 2 to 3 and curve 3 to 4 form a compound curve. By definition, the radius for curve 2 to 3 and the radius for curve 3 to 4 must coincide. Measuring back 20 feet from point 3 towards the center of curve 2 to 3 will locate the center of curve 3 to 4. Curve 3 to 4 and curve 4 to 5 form a reverse curve. The radius for curve 3 to 4 and curve 4 to 5 must coincide along a straight line between the center of these two curves. In other words, the extension of the radius from the center of curve 3 to 4 through point 4 to the center of curve 4 to 5 must be a straight line. Curve 5 to 6 and curve 6 to 7 form a reverse curve. As such, the center of curve 5 to 6 must be an extension of the radius from the center of curve 6 to 7, passing through point 6 at a distance of 20 feet from point 6. Curve 4 to 5 and curve 5 to 6 form a reverse curve. Accordingly, the extension of the radius from the center of curve 4 to 5 through point 5 must end at the center of curve 5 to 6, 20 feet from point 5. Point 8 is the PT of curve 7 to 8, located at the right-of-way of the road. The center of curve 7 to 8 must be on a line perpendicular to the road right-of-way at a location 20 feet from the road right-of-way. The radius of the transition curve. Curve 6 to 7 and curve 7 to 8 form a reverse curve. The center of curve 7 to 8, by definition, must be on an extension of the radius of curve 6 to 7, passing through point 7 and 20 feet from point 7. The various coinciding lines are added to the diagram. These lines will be used to perform calculations later. A table is set up to tabulate the curve data for the various curves. The transition curves all have a radius of 20 feet. The cul-de-sac turnaround has a radius of 60 feet. The inside radius of the curve would be the radius of the center minus 1/2 the width of the road, or 150 feet minus 25 feet, or 125 feet. The outside radius for the large curve would be the radius of the center plus 1/2 the width of the road, or 150 feet plus 25 feet, or 175 feet. Two parameters to each curve are required to calculate the remaining parameters. Only one parameter for each curve is in the table. However, the delta angle for the various curves can be calculated. The delta angle for curve 1 to 2 is found by using a right triangle formed from point 1 to the center of curve 2 to 3 to the center of curve 1 to 2 back to point 1. The angle at point 1 is 90 degrees. The distance from point 1 to the center of curve 1 to 2 is 20 feet, the transition radius. The distance from the center of curve 1 to 2 to the center of curve 2 to 3 is the radius of curve 2 to 3 minus the radius of curve 1 to 2, which equals 105 feet. The interior angle of the triangle at the center of curve 1 to 2 is found using the cosine function. The cosine of the angle is equal to the adjacent distance divided by the hypotenuse distance, or, in other words, the angle is equal to the arc cosine of 20 feet divided by 105 feet. The delta angle for curve 1 to 2 is not the interior angle to the right triangle. Rather, it is the exterior angle. Therefore, the delta angle for curve 1 to 2 is found by subtracting the interior angle from 180 degrees. The delta angle for 1 to 2 is added to the table. Previously, the angle for the large curve between the road right-of-way to the end of the curve at the start of the extension was given as 54 degrees, 10 minutes, 10 seconds. To calculate the delta angle for curve 2 to 3, the interior angle at the center of curve 2 to 3 in our previous right triangle must be calculated. This interior angle is a function of the sine. The sine of the angle is equal to the opposite distance divided by the hypotenuse distance, or, in other words, the angle is equal to the arc sine of 20 feet divided by 105 feet. The resulting angle is subtracted from 54 degrees, 10 minutes, 10 seconds to give the delta angle for curve 2 to 3, 43 degrees, 11 minutes, 20 seconds. The delta angles for curve 3 to 4, curve 4 to 5, and curve 5 to 6 are found by solving the isosceles triangle that is formed between the centers of curve 3-4, curve 4-5, and curve 5-6. The distance between the center of curve 5-6 and curve 3-4 is the radius of the curve 5-6, which is 20 feet, the width of the road right-of-way, which is 50 feet, and the radius of curve 3 to 4, which is 20 feet, for a total of 90 feet. The length for the two equal sides of the isosceles triangle is composed of the radius of curve 3 to 4, or 5 to 6, which is 20 feet, and the radius of the cul-de-sac turnaround, 60 feet, for a total distance of 80 feet. The delta angle for curve 3 to 4 is found using the cosine function. The cosine of the angle is equal to the adjacent distance divided by the hypotenuse distance. Accordingly, the delta angle for curve 3 to 4 is the arc cosine of 1/2 of the 90-foot distance divided by 80 feet, giving a delta angle of 55 degrees, 46 minutes, 16 seconds. This answer is put in the table for curve 3 to 4. It is also the same value for curve 5-6, since both angles are part of the isosceles triangle. The delta angle for curve 4 to 5 is found by determining the missing interior angle to the isosceles triangle. The missing angle of the isosceles triangle is found by subtracting the delta angles for curve 3 to 4 and 5 to 6 from 180 degrees. The delta angle for curve 4 to 5 is found by subtracting the interior angle of this isosceles triangle from 360 degrees. The The delta angle for curves 6 to 7 is determined by first finding the interior angle at the center of curve 6 to 7 within the right triangle formed between the center of curve 6 to 7 to the center of curve 7 to 8 to point 8 back to the center of curve 6 to 7. The interior angle at point 8 is 90 degrees. The length for the side of the triangle from point 8 to the center of curve 7 to 8 is 20 feet. The length of the side of the triangle from the center of curve 6 to 7 to the center of curve 7 to 8 is composed of the radius of curve 6 to 7, which is 175 feet, plus the radius of curve 7 to 8, which is 20 feet, for a total of 195 feet. The interior angle is found by the sine function. The sine of the angle is equal to the length of the opposite side divided by the hypotenuse length. The angle is the arc sine of 20 feet divided by 195 feet. The resulting angle is subtracted from the total angle that extends from the edge of the road to the start of the cul-de-sac tangent extension that was previously given as 54 degrees 10 minutes 10 seconds. The resulting value is placed in the table. The final delta angle is calculated using the same right triangle. The angle at the center of curve 7 to 8 is calculated using the cosine function. The cosine of the angle is equal to the length of the adjacent side divided by the hypotenuse length. The angle, in this case the delta angle, is the arc cosine of the radius for curve 7 to 8, in other words 20 feet, divided by the radius for curve 6 to 7, which is 175 feet, plus the radius of curve 7 to 8, 20 feet, for a total of 195 feet. The answer is placed in the table. The arc lengths are calculated using the formula for the arc length given the radius and the delta angle. The various delta angles and radii are inserted into the formula to calculate the arc lengths. The values for the arc length are inserted into the table. The tangent lengths are calculated using the formula for the tangent length given the radius and delta angle. The various delta angles and radii are inserted into the formula to calculate the tangent lengths. The values for the tangent length are inserted into the table. There is one calculation for the tangent length that is different. The tangent length for the cul-de-sac turnaround must be calculated differently. The tangents for curve 4 to 5 are shown. Since the delta angle is more than 180 degrees, the tangent distance must be calculated using an angle that is 360 degrees minus the delta angle. Failure to use the angle that is subtracted from 360 degrees will result in a negative tangent distance. The calculated tangent distance is inserted into the table. The long chord lengths are calculated using the formula for the long chord given the radius and the delta angle. The various delta angles and radii are inserted into the formula to calculate the long chord lengths. The values for the long chord lengths are inserted into the table. This completes the values for the cul-de-sac.